Is it any better now?
Yeah, it is better now.
Okay. What I will do, I will probably increase the gain of my bike so that.
Yeah, it is fine for me. Can somebody, someone from students can confirm?
Yes, sir.
So yeah,
Okay.
it's good now.
It is good.
Okay.
Yeah,
Okay.
thank
That's
you.
perfect. Perfect. So yeah. So we were discussing that what are the problems with the Newtonian picture of gravity. The first drawback was that the instantaneous propagation of the information. The example I gave was that if, let's say, mass m2 is the sun and mass m1 is our earth, then if we remove the sun because of some, let's say, some disaster, right, the natural disaster, the sun goes away, then according to the Newton's law, the earth should instantaneously know that there is no sun. But Einstein said that no information can travel faster than the speed of light. That the sun has been removed, Earth should know it within a finite time, not at the very moment, not at the very same instant. And the time taken will be the distance between the sun and Earth divided by the speed of light. So that was the one problem, one drawback of the Newtonian gravity. The second drawback was, as you can see from the simple GIF file on the right hand side, GIF image, that this is the orbit of Earth rotating around the sun, which has been highly exaggerated. That Earth is not following the same orbit. It is drifting its orbit to some different orbit. So there is a drift in the orbit, and that also was not explainable by the Newton's picture of gravity. So these observations and these questions were raised by Einstein, and then he provided a solution. Right? You should not always raise the problems. You should also suggest the solutions. Nobody is interested in listening to the problems only. So what Einstein did, he described gravity as not as a force, but as a curvature in the space-time. So this fabric, which we see, the grid kind of structure, is, let's say, our space-time. Space-time is basically a four-dimensional object, but we can here only visualizing these two dimensions. So let's say you have a mass here, and that mass will curve the space-time around it. And when you have another object which is moving in this curved space-time, it will not take the straight line path. This will take the straight line path in this curved geometry. And that is how you understand the gravity. But this is not a force, it is a particle which is moving in this curvature of in the curved space-time around that mass, particular mass. For that he gave a very, very complicated looking equation. This is not looking complicated, but if you really write them, expand them, you will see how complicated they are. So this G mu nu measures the curvature in the space-time, and this T mu nu is basically concentration of mass and energy. And we know from the special relativity that E equal to mc square, that mass and energy are basically the same thing. So if you have a mass or if you have energy concentration, then that will curve the space-time, and this quantity will basically measure that curvature in the space-time. Or in other words, if you see that there is a curvature in this space-time, then you can say that there is a mass, and what should be the mass. You can quantize that mass. So this is this equation, which is basically which is the collection of 10 coupled partial differential equations. So you can imagine. And then to obtain these equations, you need to evoke the physics in the curved space-time, which is slightly different from what we learn in our schools or in college physics. So if you get a chance sometime, you will be able to learn these things. So before going to the gravitational wave, let us discuss what are waves. Right, so there's a slight digression here. We will discuss what are the waves first, and then we will talk about what are the gravitational waves. So the waves, when we hear this word waves, few pictures emerge to our mind. These are the this is the surface of an ocean. This is a pond when you, surface of the pond when you drop a pebble into it. This is the audience, maybe in a football match or baseball match, which is trying to make a Mexican wave. And this is a simple structure which we know in our schools, right? This is the wave. This is the wave pattern, which is a very, very regular, simplest, and idealized wave pattern. This is also another example of a wave, electromagnetic wave. That now the electric field and magnetic field, they are changing their magnitude while they are moving, and they are moving in this direction at the speed of light. So this is the direction for the electric fluctuation in the electric field, and the magnetic fields are fluctuating in this direction. So can we describe these patterns, these patterns in some mathematical form? Yes, we can do that. And this is the mathematical form. This mathematical formula describes a wave, a sinusoidal wave. So you should note it down. It is different from the oscillations. This is function of both time as well as the space. This is a one-dimensional wave. This is the amplitude, kx minus omega t. K will give you the wavelength, omega will give you the frequency, and phi is the phase, some arbitrary phase. So how we characterize a wave? It is characterized by it has an amplitude, it has a wavelength or wave number, frequency or time period, it has a speed, it has polarization, it has energy, momentum, and so on. So these are some of the major properties a wave can have. So where do we get these waveforms? They are basically mathematical solutions or the physical solution of a physical system, which can be described in terms of a mathematical equation. So this is this wave equation, which is again a second order partial differential equations. Partial means because there are more than one variable, t as well as x. So this is the wave equation, which has this kind of solution. These solutions vary with x as well as time. So any function of x plus minus ct is the solution of this equation. So similarly, we should have for each wave, we should have some mathematical equation with involving the time. We call them dynamical equations. And those equations will basically be modeling some physical phenomena. So we will see different kind of waves. We see sound waves, we see electromagnetic waves, and then we see the gravitational waves also. And we know in electromagnetic waves there are various classification of electromagnetic waves depending upon their frequency. In the electromagnetic spectrum, we know that there are gamma rays, there are X-rays, there are ultraviolet rays, there are radio waves, there are microwaves which we are using for communication, and so on. So these are some classification of the waves. Mechanical waves, examples are sound waves, electromagnetic waves, light waves are an example of electromagnetic waves. And then there's another classification based on their structure. So the waves can travel as a longitudinal wave in the form of compression and rarefactions, where the medium particles are basically getting displaced along the direction of propagation of the wave. And this is the transverse wave, which travels in the form of crest and trough. And here the medium particles, they fluctuate perpendicular to the direction of the propagation of the wave. So the mechanical waves, we know, sound waves, they require a medium, and the electromagnetic wave, we know that they do not require the medium. And that's how the energy or the light from sun comes to us every day, every morning. So that was a quick review of the waves. Now coming to the gravitational waves. So they also should be having some mathematical form, mathematical structure, and they also might be the solution. They also could be coming from a set of mathematical equations. The set of mathematical equation I have already shown you, the 10 coupled partial differential equation given by the Einstein, in his general relativity in 1915, in 1905 basically. So he predicted these gravitational waves in his theory. These are one of the solutions of his equations, field equations we call them. So these gravitational waves were predicted by Einstein himself in 1915, roughly around 9 or 10 years after he gave his theory. So we know that there will be curvature in the space-time when some mass is present. The gravitational waves are basically the ripples in this curvature of space-time, which are propagating in this space-time at the speed of light. So these are the gravitational waves. We know that accelerated charges, they produce the electromagnetic waves. Similarly, these masses, when they get accelerated, they will produce the gravitational waves. And then they will travel away from these sources and they will come to us, to the earth, and we will try to detect them. The rest of the talk, I am almost halfway through of my talk, if not halfway, maybe 40%. So in the rest of the talk, we will be talking about sources of gravitational waves. Where do we get gravitation, where do they come from, and how we can detect them. And finally, we will discuss the importance of detecting them. Why this was such a big news to detect the gravitational wave. So sources of gravitational wave, there could be two sources of any kind of waves. The sources which are available on the earth, right, naturally, or they are man-made sources. So, or there are sources which we have to depend upon there are sources which are basically outside our atmosphere, outside our earth, outside our solar system, outside our galaxy, and so on. Right? So the man-made sources, they produce a very, very faint signal, which cannot be detected by any available most advanced technology. Right? For example, if I'm waving my hand, that is also a source of gravitational wave. But the amplitude, the magnitude of the signal will be very, very small. You cannot detect them. No technology is known to detect them. What we have to do, we have to depend on the astrophysical events, right? Which are very, very highly energetic and very, very violent events. For example, in this picture we saw that there was not run again. So we saw that there was two objects, and the two objects could be either two black holes going around each other, or one of them could be a neutron star, another one will be black hole, or both of them could be neutron star. So these kind of this kind of system is known as the binary system. And the name, we call them compact system. Why we call them compact? Because they are very, very dense object. So density is basically mass divided by volume. The neutron star and black hole, we know their masses could be of the order of sun, and black holes could be much, much heavier than sun. It could be 10 solar mass, 20 solar mass, and could be 10 to the power 6 solar mass also. We call them supermassive black hole. So there are black holes which are stellar mass black hole, high mass black hole, intermediate mass black hole, and supermassive black hole. And it is assumed that at the center of every galaxy there is a supermassive black hole sitting there. The whole galaxy, or everything in the galaxy is basically going around that, spiraling around that. So we saw that this was also going in spiral. Initially the two objects were very, very far away, and then they took time to come closer and closer. They keep on emitting the gravitational wave, they keep on losing the energy, and consequently they kept coming closer, started moving faster and faster. Finally they merged into each other. That phase was known as the merger. And then finally, instead of two objects, we got only one object, and that is the black hole. That black hole also had some vibrations left with it, and then slowly it loses them also in the form of gravitational wave, and that gives you the ring number. So they are binary, they are coalescing objects, and they are compact. For example, if I tell you that neutron star could be Maximum mass of the neutron star could be 3 solar mass, and the radius, the size of the neutron mass is of the order of 10 kilometers. So now imagine the sun has been shrunk, has been compacted so much that rather than having lakhs of kilometers of radii, it is now having 10 kilometers of. You can see that how much density they may have. So it's a small element, a small portion of a neutron star will weigh a lot. And why we need them, compact object? Because if they have lots of density, then they will produce lots of very high curvature in the space-time. And then when when they go around each other, they will produce the gravitational wave, which have a very high amplitude, and we should be able to detect them. So that's why we need to depend upon these extraterrestrial sources, especially the binary. There could be other sources, but these are the most promising sources, and this is the class of sources which have been detected by the gravitational wave detectors so far. No other. We are still waiting for some other sources to be detected. So how we detect the gravitational waves? When the gravitational wave they pass through the space-time, so this, let's say this was a mass of ring, which is a circular mass of ring, and you see that the gravitational wave is passing through this ring. So for first half of cycle, this ring is getting stretched in this direction. For another half of cycle, it is getting stretched in the perpendicular direction. And this is how it is doing. This going this direction, going this direction. Gravitational wave may also produce this kind of distortion in the space-time. So this, for first half it is going in this direction, for second half it is going in this direction, the 45 degree. So this shows that gravitational waves have two kind of polarization. This is plus polarization and this is the cross polarization. The gravitational wave, when they pass through, they can produce a strain in the space-time, and by measuring that strain, which is again a very faint, we can detect the gravitational wave. So strain will be delta L by L. So if L was the original length and delta L is the change in length. So this will give me the strain. Now you see the important thing, the crucial thing that should be noted down here is the sensitivity or the strain is still very low, 10 power minus 22. So this is going to be a constant. You want this to be large. For this to be large, you have to make this also large. So the target will be to make length to be larger and larger so that we get delta L also to be larger. Right? For example, if we have 1 meter L to be 1 meter, then what will be delta L? This will be 10 to the power minus 22 meter. Right? According to this formula. If this is 1 meter, this will be 10 to the power minus 22 meter, which is incredibly small length. 10 to the power minus 22. What is the smallest scale we know so far? What is the size of an atom? Can anyone answer? Yes. What is the size of atom? Anyone? Okay. The
10 to
size
the
of
power
atom
minus 10.
minus 10. Right.
What is the unit? 10 to the power minus 10 of what?
Meter.
That is
Meter.
right?
Right. So that is 1 angstrom. And what is the size of nucleus?
10 to the power minus 15.
Minus 15.
Once again, unit.
Fermi meter.
Meter.
Meter, it is
Meter.
called Fermi actually. 10 to the power minus 15 meter is 1 Fermi. Yeah.
Right. So we have been able to measure those lengths also, 10 power minus 15. Now you see how far 10 to the power minus 22 is. It is 7 order of magnitude away. So it is 1 by 10 to the power 7 times smaller than 1 Fermi. And it is an incredibly difficult task, if not impossible, to be able to measure that distance. So what we have to do, we can make this L in terms of kilometers. If we make this in terms of kilometers, then at least 3 orders of magnitude we can go up. Because if this is 1 kilometer, that will be 10 to the power minus 22 kilometers. which is around 10 to the power minus 19 meter. Right? We can make it slightly more higher, and then we can come in the order of 10 to the power minus 18 meter, which is at least 4 times higher, which is higher 4 times, having 4 times higher order of, sorry, which is 4 order of magnitude higher than the 10 power minus 22, but is still at least 1000 times the unit of the size of the nucleus, 1 Fermi. So we want to measure 10 to the power minus 18 meter, which is still a very, very small scale length. So for that we need to design some experiment, right, which is based on some physics principle, and then we have to do lots of high precision instrumentation, we have to do extreme engineering, we have to apply all kind of mathematical calculations, we have to put all our computers and computational method also to work to achieve that 10 to the power minus 18. So now this number you should keep in mind. We have to measure a change of 10 to the power minus 18 meter in 1 meter. And if we can do that, we can detect the gravitational wave. The problem is this incredibly small sensitivity. The gravitational wave, even coming from the neutron star and black hole, they will produce a strain of the order of 10 to the power minus 22, which means that space-time has a very, very stiff spin constant. Spin constant is very, very high. So F equal to minus kx. So even if its force is very, very large, k is also large, then x, change in length, will be very, very small. So the same analogy applies here. So the basic idea was that let us build a Michelson interferometer to be able to detect that small change in the length. So how do we do it? That we will first have a laser. We will throw a laser light. So this is the source. So this laser light is nothing but an electromagnetic waves which are propagating. And then we will have a beam splitter. This beam splitter will divide this laser light into 2 equal beams and make them go in the perpendicular direction. So this is at 45 degree. So one part will go in this direction, another part will go in this direction, and they are mutually perpendicular. So laser light will go for a long length, and this long length is basically of the order of kilometers. To be precise, it is 4 kilometers long. So laser light will go and will hit a mirror which is 4 kilometers away from the beam splitter, and from this mirror it will get reflected, will come back, will get reflected, will come back, and they will join here, and then they will make an interference pattern. That interference pattern will be recorded by this light detector, the photodiode. Now if the gravitational, so initially the 2 arm length were same, 4 kilometers each. Now when the gravitational wave passes through, look at this picture. So one arm will get stretched in this direction, another arm will get squeezed in another direction. So let's say this gets extended and this gets squeezed. So initially the path length was same, was 0. Now there will be a finite path length. And we know from our school level that interference pattern is function of the path difference. So because of the change in the path difference, this interference pattern will change. And the interference pattern change, which means that your light detector or the photodiode will detect the different light, and it will convert it into electromagnetic signal. And that will be different when there was no gravitational wave. So when we see the fluctuations in the interference pattern, which was set to some value, and we call that as the reference interference pattern, once the gravitational wave passes through, there will be a change in interference pattern, and then we will immediately know that some gravitational wave has passed through our interferometer. And this kind of device, this is the basic principle, and this kind of device are in operations, and they have detected the gravitational wave and they are called as the LIGO. Right? Laser Interferometric Gravitational Wave Observatory is the full form. So this is the basic principle, but in order to detect the gravitational wave, it takes a lot of effort. Because not only gravitational wave will pass through it, many other things will happen. There will be different kind of noises present. So this is the next slide. This is the aerial view of one of the detectors. I think this is the Hanford site. I'm not sure, maybe Livingston. So there are two detectors. So this is the aerial view. This is where you have your central assembly. And this is the arm length, 4 kilometer arm length. This is another 4 kilometer arm length, which is perfectly perpendicular. And then this is how they are operating. So currently there are 3 detectors in operations, 2 LIGO detector and 1 is Virgo detector, which is a joint collaboration of European countries, I guess. And there will be 2 upcoming detectors. One will be in India, so we are fortunate enough to have 1 detector in our own country. Another one is also ready. Yes, I think that coming to picture this year itself, and that is the Japanese detector. We call it Kagra. And then one more space-based telescope is also proposed. That will be called as the Einstein telescope, which will have a very large arm length. So these LIGO currently they are 2nd generation detector, and that will be called as the 3rd generation detector. Yeah, so the issues with the detections are these. Noises, the class of noise, which your gravitational wave detectors may suffer with. Seismic noise, right? We know that this site may not be quiet. Lots of seismic events might be happening inside the surface. Earth, we know it's a very active environment below the surface. Outside it looks very quiet, but below the surface there are lots of activities happening. Sometimes they give rise to the earth shaking, earthquake also. So those small vibration, and you know earth is also going around. But mainly the inner activities, internal activities inside the earth are basically responsible for those surface shaking. And when the surface shakes, because you intend to measure such a fine distance, even that shaking will provide you that kind of confusion, or that kind of impression that you have detected the gravitational wave. And that may not be the true gravitational wave. That could be because of this seismic activity. Thermal noise, another one. The mirrors we are using, the beam splitters we are using, they may have thermal noise because the laser light will be passing through the surfaces, and the surface atoms, they will be in the Brownian motion. They may also deflect your light to give an impression that you have detected the gravitational wave. Because all you have to record is a small change in path length, the finest change in the path length. And that could be produced by any of these things listed here. Short noise, radiation pressure noise. If you're interested, you can learn more about it. And gravity gradient noise, gravity will not be uniform. There could be change in gravity. When you go from this point to this, because you have to go for over large distance. 4 kilometers is a large distance, and gravity may change there. And apart from these physical processes, there could be some instrumentation and environmental glitches also. For example, you are using laser, you are using various pumps, you are using various motors and so on for vacuum and other things. They may also disturb your beam splitter or mirror to give you the false impression of detection of gravitational wave. This is so sensitive that even if you pass through this site on a car vehicle, then that is also not good. Even the aeroplane, if that passes over this site, that may also produce sub-signal, and that's what we call it glitch. So you need a site which is seismologically inactive, and then all kind of activity should not be there. Vehicle should not be allowed. There should be no airport nearby and so on. So these are the technical challenges. Not only technical challenges, the Einstein equations themselves are so complicated. To understand what will be the nature of gravitational wave, right, where they might be coming from, to do those calculations itself is a challenge. And computational challenges are also there, right? because those are partial differential equation, 10 couple, and it is not easy to write the numerical codes for them to solve and see that this is how they will behave. Another most challenging thing is that signal to noise ratio will be very, very large. You cannot directly see that this is the gravitational signal. You can see. You cannot record a gravitational waveform. It is buried in the detector noise. You have to apply the very sophisticated data analysis methods also to fetch that signal out of the noise. And this is true with most of the astronomical observation, let it be the observation of exoplanet, let it be. In solar, signal to noise ratio is not that poor, but in other part of the astronomy, even in the electromagnetic observation, for example, radio astronomy, X-ray astronomy, same thing you are doing. You have got a data and you have to analyze it using some statistical and computational tool. And there is a beautiful branch on that, which is known as the astrostatistics, which is basically a collection of statistical methods to analyze the data. Why only in astronomy? Even in the CERN, which is a large hadron collider, where the two energetic particles, they are smashing into each other, so that we know what a matter is, what is the fundamental constituent of the matter, whether it's an electron, whether it's a quark, or even a smaller entity. So there also you get this data, and you have to use the data analysis tools, write the computation program to get the information out of the data. So yes, despite all the challenges, we discovered the gravitational wave, and it was received by the detectors on 14 September 2015. Call that 150914. So yeah, as I said that you did not see on your oscilloscope that this is the gravitational signal. You basically plotted some figures, right? And this figure basically comes from that you detected the gravitational wave. So this is the gravitational wave, which is much beyond than all the noises. So this is what you can understand from here. This was the date when it arrived the detector. It is coming from very large distance, 410 megaparsec, right? And it was two black hole events. The total mass of the black hole was, one was 39 solar mass, another one was 31 solar mass. So 70 solar mass, and the final black hole was 67 solar mass. So typically, the 3 solar mass energy was released in this gravitational wave event, which is 3 times larger than what sun will radiate in its lifetime. So you can say how energetic these events are. And they are coming from 410 megaparsecs. So these were the events. The collision happened some billion years ago. And because the speed of light is finite, so from 410 megaparsec, it took us some billion years to come to the Earth. And it made a big news, right? Lots of tweets were there from our own Prime Minister, the President that time, Barack Obama, and the newspapers were filled with these news, and Amul also had a cartoon on this. So I will put some facts so that you appreciate that why it was a difficult and such a rewarding task. Because the gravitational wave were predicted by Einstein in 1915, and they were detected exactly after 100 years. The efforts were started in 1960s to detect the gravitational wave, where the scientist Joseph Weber, he built a detector. This was not an interferometric detector, that was basically a bar detector, right? Which is different from this. And then in 1970s, a group of people led by Kip Thorne, Donald Drever, and Rainer Weiss, they started this project. And this project was funded by the National Science Foundation. And the total cost, this is an old figure, total cost by the time gravitational wave was detected was around $620 million. First detection, second detection, it was a joint effort. There were 1,000 scientists coming from the 80 institutions across 15 countries working day and night on the experiments, on the data analysis. So this was a big deal. And then these three people, not the driver, the driver was basically no more at that time. So the Nobel Prize was shared by Ray Weiss, Kip Thorne, and Barry Barish. And it was given to them for their decisive contributions to the LIGO detector and the observation of gravitational waves. Right, so the last point, why the gravitational discovery is important. So far we have detected 19 events, and this is altogether a new window to look at our universe, because all the information which was coming to us was coming from in the form of electromagnetic waves. This information, this is the first time we have detected the gravitational wave, and they carry the information which is complementary to the electromagnetic wave, which is different from what electromagnetic waves can tell us about the universe. For example, the first discovery told us that was a direct confirmation that black holes exist, they exist in the binary, and they really merge. They take a time. They do not basically keep on coalescing for infinite time. They do merge, and then there is a merger and ring down phases also. So the prediction which was made by Einstein and later by many people for around 100 years, they all were confirmed by this gravitation. So this is a new way to look at our universe, and this will definitely bring this will unravel lots of mystery of our universe. Later in 2017, we detected the two neutron stars going around each other, in addition to the two black holes. And these neutron star events also produce the electromagnetic wave signals, which were followed up by various electromagnetic telescopes, and they confirm the discovery by the gravitational wave. So now you got two signals, one in the form of gravitational wave, and the same event also gave the electromagnetic observation. So that was also the beginning of multi-messenger astronomy with the gravitational wave. And this is the interesting fact that people calculated that this collision of neutron star is also a test lab where lots of the heavy elements were formed, including gold and platinum. So when they smashed into each other, gold of mass having around 100 times the Earth's mass was produced, and platinum of 500 times the Earth's mass was produced. So these are very exciting time with the detection of gravitation. Yes?
Sir, can you just repeat the statement of the gold and platinum?
Very good. Do you have some jewelry shop or what? You are too much fond of this. The statement is that these neutron stars, they are very, very compact elements. The solid we know, the density of gases, which is low. We know the liquids, they are more dense than the solids. We know the liquids which are more dense than the gases. And then solids, they are most dense among the solid, liquid and gas. Neutron star is far more denser than the solids we see on the Earth. These are very, very exotic matter. We generally do not know what they are made up of, because I told you their density is very, very high. The mass around this solar mass is basically put into a 10-kilometer radius. So what physicists had postulated, they have proposed that when the two neutron stars collide with each other, they will produce the heavy elements, heavy elements which are there in our periodic table, right? Stable heavy elements, and gold and platinum are also one of them. So people did some calculation based on the models available, and then they said that when these two neutron stars collided, around 100 times mass of the Earth, gold would have been produced. And the platinum was also have been produced, which is around 500 times the mass of the Earth. So people suggest that this is the event because of which we get the gold and platinum, whatever we have on Earth today. Is something of this kind might have happened. So there are lots of chemistry also you can do with this. But this is the chemical process. Right? We know how, in the chemistry also we know, right? If you want to change one element to another element, it is basically the proton. That is the inherent property of any element. If you change the number of protons, then element will change. So in principle, you should be able to convert your copper into gold by adding few more protons, or iron into gold by adding or removing some more protons. But because you have to do the nuclear transformation. But in theory, it is something else. Doing it in lab or experiments is not that straightforward. Lots of challenges you face when you do something in the laboratory. So lots of chemistry can also be done here. So did I answer your question?
Yes, sir. Thank you, sir.
So multi-messenger astronomy, as I said, that now we have gravitational waves, electromagnetic waves we already having. Neutrinos are also known as cosmic rays are also known. They are again energetic waves with a very high energy, and we do not know their origin. We say that they might be coming from far away from the cosmos. So now we can basically do the astronomy with all these four kind of signals. And this neutron star even told us that the gravitational wave and electromagnetic wave events, the signal could be combined, which means that black holes or neutron star, NSBH or BNS, could give you both gravitational wave as well as the electromagnetic wave. So you can put both the detectors in that direction. One will detect the gravitational wave, another one will detect the electromagnetic wave. But I made a wrong statement here. Gravitational waves are basically omnidirectional antenna. We do not need to point them into particular direction, but we know in the electromagnetic waves, they are pointed antenna, right? We need to point them in a particular direction, especially the radio waves, the TV we have. Right? It is also connected. We have a dish antenna, and which collects the signal coming from a particular direction. We cannot leave it in any direction. So these are not electromagnetic detectors, are not omnidirectional detectors. So yeah, what is there for the students currently? There are many things, right? If you want to join the theory, you can join the theory. You can do lots of complicated mathematical calculation. These are known as the post-Newtonian calculation, which are really, really challenging. The best brains are working to do these calculations. Not everybody can learn those things. Numerical relativity is another challenging area. In experiments, you can see, I told you that lots of sophisticated components are there in a gravitational wave detector. Even if you were to remove or even a single noise, let's say on seismic noise or thermal noise, or maybe designing the laser for that particular experiment, or maybe the vacuum tube, 4 kilometer long vacuum tube, or material for the mirrors, beam splitters, assembly where the gravitational wave will be put, or how to isolate the seismic noise, thermal noise. Lots of challenges are there for doing things for the experimentalist. In computational tools, I have already mentioned that you need to apply the methods of the current method of data analysis, because data is also huge. The gravitational detectors, they run for months and they record the data at the rate of a few megabytes per second. Now you can multiply second with the minutes, with the hours, with the days, with the months, and see how many bytes you will get. So to store that data, to transfer that data, to process that data, to analyze that data, lots of sophisticated big data tools are required. So there is an opportunity for everyone: physicists, mathematician, statistician, engineers, and computer scientists. It is a mega project. In India also, you can join. Finally, I will leave you with some suggestion where you can look at. The first one is the website for the LIGO MIT group. Second one is the India group, Indigo or LIGO India. Third one is, I think this website might not be working. You can search for Gravitational Wave Open Science Center. And if you have any query, if you want to know something, if you want to need more information, you can write to me. The images I have taken from the Google, and due to the shortage of time, I could not give the individual references, but most of the images have been taken from the Googles or from the research papers. And yes, there is a quote to end with, which Stephen Hawking said, that black holes may not be completely black, which means that some information can come out of them, and that information may let us know what is inside the black hole. Thank you very much.
Thank you, Dr. Gaur.
Thank you, sir.
In fact, your last, quote, the black hole may not be completely black, reminds me of one statement from, thermodynamics. Black body must not be black, not necessarily to be black.
Right.
So, students, the session is open, and the session is not only open for students. You can also ask questions, Dr. Gaur.